Dinosaurs ruled the Earth for 150 million years, surviving, evolving, flourishing. Then mysteriously, they vanished. To find out why, scientists searched the void of outer space. They combed the hot sands of the desert. And they plumbed the depths of the ocean. Some believe the answer is locked up in chunks of amber. Everywhere they look, they're finding compelling clues about why the Earth was once ruled by dinosaurs. And then there were none. 65 million years ago, the world was teeming with dinosaurs. But then an unimaginable disaster happened. A giant asteroid came screaming toward Earth at 60,000 miles per hour. It burst through the atmosphere and smashed into the planet. Fiery debris was thrown thousands of miles, causing death and destruction. Smoke and dust formed a giant cloud that enveloped the Earth, blotting out the sun and drenching the land with lethal acid rain. The planet was plunged into icy darkness. Photosynthesis stopped. Vegetation withered. In the gloom, plant-eating dinosaurs starved to death. The meat-eaters soon followed. In one swift, terrible catastrophe, the dinosaurs' 150 million-year reign came to an end. It's a compelling story and a popular notion. But is that the way it really happened? Many scientists believe it's only part of the story. They feel that an asteroid impact alone couldn't have caused the extinction of the dinosaurs. Their quest for a hidden lethal factor behind the extinction has led them to look in the most unlikely places, even the bottom of the ocean. Today, a research team is heading toward the coast of Mexico on board Juárez Resolution. Once an oil drilling ship, now converted into the world's biggest and most technologically sophisticated floating lab.
From the crater to the south of the
University of Rhode Island oceanographer Harold Sigurdsson is taking his team close to the site of the asteroid impact, now partially buried beneath the sea. He's convinced that the only way the blast could have wiped out the dinosaurs was if it struck extremely rare terrain. To prove it, he's searching for something peculiar in the sediment where it hit, something that made the effects of the explosion more deadly to the dinosaurs than the impact itself. The team will use the ship's massive drill probe to bring up narrow columns or cores of sediment from the ocean floor. Each core consists of dozens of seabed layers that accumulated gradually over millions of years.
We're planning to drill at a number of sites in the Caribbean where we will recover cores from the sea floor about a mile down. that will provide us new information about the process of the impact and the environmental effects of this great meteorite impact.
Aboard are 10 state-of-the-art laboratories where the scientists will analyze the chemistry of the rocks and sand in the cores.
Boundary layer clay in it.
There's a lot of work ahead, but when they finish, Sigurdsson may finally have the answer to the dinosaurs' demise. It's a mystery scientists have been trying to figure out ever since dinosaurs were discovered. British naturalist Richard Owen coined the word dinosaur in 1842 and also came up with the first theory for why they died out. He believed that in the age of dinosaurs, there was a depletion of oxygen. The dinosaurs survived because they were like sluggish reptiles. Then somehow oxygen levels rose, favoring the faster-moving mammals, and the dinosaurs went extinct. But Owen's theory was little more than guesswork, and since Darwin had yet to publish his theory of evolution, most of Owen's contemporaries believed in a simpler notion, that the dinosaurs were wiped out by the biblical flood. As science progressed, geologists found evidence of numerous great floods and catastrophes in Earth's history, floods that the dinosaurs survived. At the turn of the century, another idea emerged, that the dinosaurs, like all other extinct creatures, were meant to die out and give way to more advanced forms. Throughout the 20th century, many theories were bounced back and forth. However, all had one thing in common with earlier ideas. They couldn't be supported by hard evidence. Then, in 1978, in a limestone gorge in central Italy, a geologist named Walter Alvarez made a discovery that took the dinosaurs' extinction out of the realm of guesswork. Alvarez noticed a strange thin dark line of clay between two layers of sediment, dating back roughly 65 million years. Below the unusual clay is limestone from the Cretaceous, a period in which the dinosaurs were thriving. Above it is the Tertiary period, when all the dinosaurs and many other life forms disappeared from the fossil record. Because the layer divides these two geologic periods, it's known as the KT boundary. The C was changed to K because C had already been used to describe another geological time period. Alvarez brought a sample of the thin clay layer back to the lab for analysis. There, his team discovered something strange. It had over 30 times the normal concentration of a rare metal called iridium. Stranger still, other researchers soon reported the same clay layer at sites around the world, always loaded with iridium. Then, with the help of his father, a Nobel Prize-winning physicist, and other colleagues, Alvarez came up with a daring new theory. Since iridium is rare on Earth's surface, but common in asteroids, he deduced that 65 million years ago, a 6-mile-wide asteroid slammed into the Earth and vaporized, showering the globe with clouds of iridium-rich dust and other debris. Because this phenomenon coincided with the extinction of the dinosaurs, they developed the now well-known scenario for the dinosaurs' sudden death by a killer asteroid. But critics were quick to point out that iridium at that level isn't found only in asteroids. It's also in the Earth's core. So maybe the dust clouds spewed from volcanic eruptions. Scientists have found evidence of extraordinary lava flows in India that coincide with the dinosaur extinction. But it's uncertain whether the eruptions were vast enough to cause worldwide extinction. Meanwhile, if Alvarez and his supporters wanted to prove their case, they needed to find a huge crater somewhere on Earth's surface. According to their calculations, it should be about 112 miles in diameter and 65 million years old. Soon, several candidates were spotted, one in Canada, another in Iowa. But the Canadian crater was too old, and neither crater was big enough. Then, in 1990, the elusive crater was finally discovered just off the coast of Mexico's Yucatan Peninsula, mostly beneath the Caribbean Sea. It was named the Chicxulub crater. Though the crater had been found, a crucial question remained. Was the impact alone enough to cause the extinction of the dinosaurs and half the life on Earth? The team aboard the Juarez Resolution is out to prove that it wasn't. Their leader, Harold Sigurdsson, thinks there was more to it. His team is here in the Caribbean Sea to explore sediments from the KT boundary that surround the submerged Chicxulub crater. They're hoping to find evidence that the rock layers hit by the asteroid were rich in sulfur, which would have worsened the aftermath of the explosion. The research ship will drill not into the underwater crater itself, but into several spots on its periphery. When the asteroid hit, it first threw out dense, fiery rock and debris for thousands of miles before the finer particles floated into the atmosphere. The heavier ejected material at the KT boundary is what interests Sigurdsson.
One of the objectives of our expedition is to drill into the seafloor in the Caribbean in order to recover material from the boundary layer or from the deposit that was ejected by this great impact.
The drill team pushes a pipe thousands of feet long through a hole in the bottom of the ship. On the end of the pipe is a drill bit with super hard tungsten carbide teeth that can chew through rock. A sonar beacon sends sound waves to the ship, guiding the drill into a cone already set on the seafloor. To reach a mile down, they have to assemble the pipe on board, linking 100-foot sections together one by one. Sand and rock layers beneath the ocean floor get pushed up the pipe to form a core that the scientists will study. To retrieve just one sample, it takes a total of 4 hours. When they pull the drill back to the surface, the core will have the same layers in the same order as the undersea rock itself. But the KT boundary layer they're looking for is thin, making it extremely difficult to locate beneath a mile of water. Will the team find it? There's no way of knowing until they get the core into the lab. The team aboard the Juarez Resolution anxiously awaits the retrieval of a core containing sediment from the seafloor. If it holds the crucial KT boundary layer, they'll begin to look for evidence that the killing power of the asteroid that wiped out the dinosaurs was amplified by its collision with sulfur-rich rocks. After the core is recovered and cut into manageable sections, it's sliced down the middle at the splitting station. Half will be saved for later study. The other half goes directly to the onboard lab.
Well, see what we got here. Looks like a great core.
Now, Harold Sigurdsson and his team can examine the core to see if it contains the dark clay boundary layer. The drilling was a success.
If this is the tertiary limestone,
The layer is right there in the middle of the core.
in order to pin that down.
Well, we need to get a sample from somewhere down in here. We should see. It might be in the upper part of this.
One end is from the Cretaceous period, when the dinosaurs were still alive. The other end is from the Tertiary, after they died out. And in between is the KT layer that marks the dinosaurs' last days on Earth. But Sigurdsson leaves nothing to chance. He has to be sure that he's really found debris thrown from the impact. For that, he'll study a sample under the microscope to look for the unmistakable signs of an asteroid explosion. The energy of such a blast is so enormous, it melts the underlying rock. Globs of liquid rock are flung into the sky. The molten rock cools as it falls to Earth. Some turns into tiny glass beads, or tektites, which fall like rain all around the Earth. At the same time, the blast shatters grains of the mineral quartz in a distinctive way. It's called shocked quartz. Under the microscope, they find the shocked quartz. It's clearly sheared and shattered by the force of the explosion. Then they find the distinctive glass beads, the tektites. The two discoveries prove they pinpointed the ejected material. Now Sigurdsson and his team can begin to analyze the tektites for sulfur content. Careful chemical analysis later shows that Sigurdsson found what he wanted. The tektites contain a high level of sulfur, indicating the asteroid struck sediment that was rich in a mineral called gypsum. According to Sigurdsson, the energy of the impact would have vaporized the gypsum into a huge cloud of sulfur dioxide. As it spread through the upper atmosphere, it changed into sulfuric acid. Particles of the sulfuric acid acted like trillions of lenses, reflecting the sunlight away from the Earth. The deadly veil would have blocked out sunlight to a greater degree than anyone imagined. For an entire year, the world must have been dark and frozen, leaving no chance for the dinosaurs to survive. It was an incredible twist of fate that the asteroid hit where it did. It was like a bomb hitting a powder keg. Even more astonishing, less than 1% of the Earth's crust has this kind of sulfur-rich rock. If the asteroid had hit almost anywhere else, the dinosaurs might have survived. In the ship's lab, the team finds evidence of the impact's effect on creatures that lived in the sea, where apparently even more life was wiped out than on land.
Here in the lab on ship.
University of Rhode Island paleontologist Stephen DeHunt put limestone from the core under a microscope.
If you take a look at the rock that's below the impact layer here, you see the skeletons of small animals that floated around in the surface ocean eating phytoplankton. This rock is composed almost entirely of their skeletons. We have, in this picture, probably 8 or 9 different varieties, same size.
But just a centimeter above the impact layer, a totally different world appears.
We see a rock that's just got a few scattered, lonely little individuals here and there. These 3 dots right here comprise the skeleton of one of the few species that actually survived the impact event. Before, the ocean was filled with all these other varieties. After the event, nothing left.
So an ocean teeming with life suddenly became barren and empty. One cosmic mishap forever changed life on Earth. To Sigurdsson, it all adds up to proof that a massive asteroid blasted into a bed of sulfur-rich sediments and wiped out ancient life on Earth in a flash. It's clear that the dinosaurs didn't stand a chance in the bitter aftermath of the impact. But exactly how close did the asteroid come to destroying all life on Earth? Clues that reveal the magnitude of the devastation are buried in the bleak badlands of North Dakota. Here, summer temperatures reach over 100 degrees in the shade, and fierce storms whip up the sand. But scientists flock here because of its well-preserved record of the end of the dinosaur age. Today, a team is setting out to learn more about that record. Leading them is Kirk Johnson, a paleobotanist from the Denver Museum of Natural History. He's here to look at the fossil record of plants. An asteroid powerful enough to kill the dinosaurs would have also destroyed a tremendous amount of plant life. In the rocks, he has little trouble finding the thin, dark clay layer that marks the impact, the KT boundary.
This little thin layer here, it's about ½ an inch thick. It's dark gray to black, appears as though it was deposited in less than a year. It looks like it's the fallout layer from an asteroid impact that occurred in Mexico.
With the impact layer identified, Johnson and his crew search for plant fossils. To him, they can actually reveal more than dinosaur bones.
The plants that grew with the last dinosaurs actually tell you a lot more about the late Cretaceous period than the dinosaurs themselves, because plants are a much more integral part of the landscape. When you walk outside, for instance, what do you see? You don't see lots of animals running around. You see vegetation, plants, trees, grass.
To get a clear picture of what happened to the vegetation at the KT boundary, the team must find a wide sample of plant fossils.
We have to set the stage. We have to build the late Cretaceous world before we destroy it. And the destruction of that late Cretaceous world is what happened right at the KT boundary. And what we're trying to do here is reconstruct the vegetation, the landscape, the environments of the late Cretaceous, understand its climate. Then what we do is climb up the hill, we cross the KT boundary, we do the same thing in the early tertiary period, and we compare before and after.
The team first works in sediments from the late Cretaceous period, the time just before the impact. They'll soon find out what kind of landscape the dinosaurs roamed in and what happened to it after the asteroid hit. By finding plant fossils from below the KT boundary layer and comparing them to what's left above, paleobotanist Kirk Johnson and his team hope to discover the destructive power of the asteroid that caused the dinosaurs' extinction. As the soft rocks from the late Cretaceous layer are pried open, they reveal a variety of fossilized leaves. Impressions of plants that once provided food and shade for the dinosaurs are exposed for the first time in millions of years. Most are broadleafed, like relatives of avocado, cinnamon, and lotus plants. All are subtropical species. Even a palm tree turns up.
This is a 66-million-year-old palm frond. So we're looking at a fossil that was a tree 66 million years ago, and that means that 66 million years ago, North Dakota wasn't cold in the winters. It was warm in the winters, and it was warm in the summers. It was a subtropical climate.
In the final days of the dinosaurs, this part of North Dakota was a lush forest. And the soft sandstone the fossils are found in tells Johnson that a stream once ran through this area. The fossils formed when leaves dropped into the stream and were buried by sand. Over time, the stream dried up and sandy layers slowly turned to rock, while minerals entered into the leaves and turned them into fossils. What's left millions of years later is a record of the once green and steamy landscape that dinosaurs lived in. But then the asteroid hit, and everything changed.
After the boundary, the plant species diversity plummets. It's a real barren wasteland up there. I mean, it's still forests, but the forests have 5 or 6 different kinds of plants. Down here in the Cretaceous, 60 or 70 species of plants.
Having collected more than 20,000 fossil leaves from above and below the KT boundary, Johnson calculates that 80% of the plant life here disappeared after the impact. Proof that the asteroid wiped out not just the dinosaurs, but entire ecosystems. Still, a mystery remains. Many small creatures made it through the crisis. Unlike dinosaurs, their fossils appear above the KT boundary.
We find our crocodiles, alligators, turtles, snakes, lizards, and mammals, and birds, frogs, things like that. But all small animals, and one of the things that all small animals share, besides their small body size, is they have pretty large populations. So there's a lot more mice than there are elephants, for instance. And so that's one of the things that probably made the dinosaurs vulnerable, was the fact that they were large animals, and as a result had probably relatively small population size.
So, does a solution simply lie in the large numbers of little animals, guaranteeing that some would survive the harsh aftermath of the impact? Or was there something else going on? Even today, the puzzle of the dinosaurs' disappearance remains unsolved. Scientists still bitterly dispute the cause. The asteroid theory may be popular, but many don't accept it. By probing further, they've found clues hinting at other agents of death and offer explanations as to why some creatures survived. At the Tate Museum in Casper, Wyoming, one of paleontology's most original thinkers, Bob Bakker, has devised his own solution by looking at the big picture.
We dinosaur scientists have a KT fixation. There are conferences about the KT, there are books about the KT, there are TV programs about the KT. That's a bit of a mistake, because if you want to know why the dinosaurs died at the end of the Cretaceous, you got to put them in context. That wasn't the only ecosystem collapse. There were 5 or 10 or 15 others. You've got to study the KT by comparing it to the end of the Jurassic, and the end of the Triassic, and the end of the Permian, and the extinctions that hit animals long after the Cretaceous. Put the KT in context, and then you'll find out who killed T-Rex.
Besides the dinosaurs, there have actually been at least 5 mass extinctions throughout the history of our world. In fact, extinction seems to be the rule. Many scientists agree that 90% of all creatures that have ever lived are now extinct. Studying these mass extinctions, Bakker found that they all had something in common. He uses the Jurassic extinction as an example.
At the end of the Jurassic, this system collapsed. The top predators, the allosaurs, went extinct. Their prey, the brontosaurs, were nearly totally exterminated. The plant-eating stegosaurs became very rare. In the oceans, there were extinction. What did it? The pattern of dying is the same you see at the KT boundary, the end of the Cretaceous. In fact, every time there's an extinction on land, it happens the same way. The victim profile is the same. It's the big active predators and the big active plant eaters who die. There would be extinctions after the KT. There were extinctions before the Jurassic, and all of them have the same MO, modus operandi. You want to know why the allosaurs went extinct? You have to find the serial killer that attacks the land ecosystem.
What caused the large dinosaurs to die at the end of both periods? According to Bakker, every extinction has coincided with a drop in global sea levels. This left land bridges connecting previously isolated continents. Dinosaurs that were living on a single landmass could then easily spread from one continent to another, but they carried with them latent diseases from their own habitats. When they came in contact with groups of dinosaurs from new habitats, diseases would be transmitted. Without immunities to new diseases, one group would be killed off by an epidemic. Eventually, entire populations would collapse. But what about the smaller animals? According to Bakker, it was easy for large dinosaurs to roam long distances across land bridges, but difficult for small animals. Even a shallow river could block their progress. With the big dinosaurs gone, niches opened up for those who hung on. In the hills of Como Bluff, Wyoming, Bakker has found evidence of survivors of the Jurassic extinction, which shows a similar pattern to the extinction at the KT boundary.
The extinction of dinosaurs at the end of the Jurassic was an opportunity for other species. If you lived in fresh water, if you were a turtle or a crocodile, you enjoyed the event. Turtle evolution speeds up during this extinction time. And if you were something else, too, you enjoyed the event. If you were small and hot-blooded and furry, if you belonged to our class, the class Mammalia, your evolution, too, took advantage of this opportunity.
So each time an extinction occurs, opportunities are created for the survivors. For another scientist, the surviving creatures at the KT boundary provide evidence for another novel theory of the dinosaurs' demise. He believes they weren't killed by a sudden asteroid explosion or disease, but by something in the air.
Now we can just gently tease.
Every summer, paleontologist Keith Rigby of Notre Dame University comes to the Badlands of Montana to hunt for fossils.
Okay.
What he finds here tells a different story of the dinosaurs' extinction 65 million years ago.
We're looking right here at what some say is the Cretaceous-Tertiary boundary, the black streak in the hillside right here. Some say this is where an asteroid hit the Earth, killed the dinosaurs, and everything was wiped out in more or less an afternoon. What we're finding out is that it's different than that.
The startling evidence he's found is the product of extensive teamwork. His students and volunteers aren't looking for prize museum specimens. Instead, their goal is to collect thousands of tiny bone fragments and teeth from many creatures. These will allow Rigby to build a broad picture of entire animal populations. He thinks tracing how these populations changed over time is the best way to study the cause of the extinction. It's demanding work. Every day, his diggers shovel out a couple of tons of dirt. But this is no ordinary dirt. It comes from near the KT boundary and contains hundreds of small fossils. Some of the sacks are filled with sediment taken from below the boundary in the Cretaceous period. And others contain sediment from above in the Tertiary. Each is carefully labeled.
Out of it now.
The team hauls the bags to a nearby reservoir.
Go to the right.
Here, the contents of the sacks are emptied into strainers. Each layer is kept separate. Next, it's time to head for the water. The water rinses away the sand and clay so that only hard material remains. Mostly rock turns up, but tiny broken up fossil bones and teeth are also revealed. Back on dry land, the rocky debris is picked out, leaving only fossils. Finding these fragments is the hardest part of the work. The trick is knowing which are rock and which are fossil. It takes a discerning eye. Though the fossils aren't much to look at, there are lots of them from a wide range of ancient animals. Not only dinosaurs, but alligators, salamanders, turtles, even tiny mammals. Back in the lab, the bones are sorted according to whether they were found in Cretaceous or Tertiary layers. Then they're organized by species. This will give Rigby an indication of which animals survived the KT boundary event and which did not.
No, I'm just putting it up there.
By tracing the fate of a wide variety of animals, Rigby creates a kind of snapshot of the entire living world in the Cretaceous and Tertiary periods. If there was a sudden catastrophe, it should show up as a clean break in the fossil record of many species at the KT boundary. But in fact, Rigby has found just the opposite. His work shows that the dinosaurs' extinction unfolded slowly, too slowly for an asteroid to have been the cause, and was already underway long before the asteroid hit. What's more, Rigby discovered that the smaller animals that became extinct around the time of the impact did so gradually, not in one single swift moment. At the same time, other species survived unharmed, and most surprising, small mammals began to diversify and expand. So even though Rigby accepts that an asteroid hit the Earth 65 million years ago, he's convinced that other factors have already set the wheels of extinction into motion. In fact, according to Rigby, the entire idea of sudden extinction as seen in the rocks is misleading. A layer marking an extinction may be less than an inch thick, but could represent tens of thousands of years.
We've seen extinctions in the geologic record time and time again. They appear sudden in the geologic record, but this is thousands, tens of thousands of years to take to accomplish this sudden geologic event. It takes time. It appears suddenly in the geologic record, but in our frame of reference, in our lifetimes, it's many generations, 10,000, 100,000 years, condensed to appear in the geologic record as sudden, but in reality is quite a long period of time.
But if dinosaur extinction was already underway long before the asteroid hit, what caused it? Rigby and his colleagues have come up with a clever and controversial answer. He thinks the solution lies inside chunks of amber. But this is no Jurassic Park. He isn't trying to bring back the dinosaurs. He wants to figure out why they disappeared. Amber is formed from hardened pine resin, a protective substance found on the surface of trees. The sticky resin flows down the tree, trapping bugs, dirt, even bubbles of air. After a while, it solidifies, preserving everything inside. In its fossilized form, it's called amber. Rigby's team has dug up chunks of amber preserved inside layers of rock from the Cretaceous, the last period of the dinosaurs. What they're looking for is amber chunks that have bubbles trapped inside. The bubbles, they believe, contain the air breathed by dinosaurs millions of years ago.
The clues that we found so far are incredibly interesting. We found that the atmosphere of the last of the dinosaurs is dramatically different than what we have now.
Could the air that dinosaurs breathed be different from today's? To find out, Rigby sends off the chunks of amber from his dig site to a lab in Denver. There, Gary Landis, a geochemist from the United States Geological Survey, will release the air from the bubbles for the first time in millions of years.
It's nothing short of phenomenal. It's really exciting. I mean, to hold a piece of a capsule that contains air from 60, 70, 100 million years ago is phenomenal. It's thoroughly thrilling.
But how can Landis be sure the air inside the bubbles is really that old? The ancient air may have leaked out, or new air leaked in. To show that amber is airtight, Landis devised a test. First, he placed samples of amber inside a nuclear reactor. The radiation converts potassium, found naturally in the amber, to the gas argon. Argon molecules are smaller than oxygen molecules and don't react with amber, so argon would escape from the amber more easily than oxygen. After monitoring the samples over a 3.5-year period, Landis found that the argon did not seep out, proving that amber is leak-proof. The next step is to release the air to analyze its contents and see what secrets it tells about the fate of the dinosaurs. To do that, Landis puts amber from the Cretaceous inside a vacuum chamber. The machine slowly cracks and crushes the amber, unlocking the ancient air trapped in the bubbles. He then uses a mass spectrometer to measure the different elements of the air and identify its components. The results show the air breathed by the dinosaurs during the Middle Cretaceous was made of the same elements as today's. But there was one crucial difference. The amount of oxygen was dramatically higher, at nearly 35%. The air we breathe contains only 21% oxygen. By analyzing air samples ranging from the early Cretaceous to today, Landis found that oxygen levels have gradually dropped. Landis and Rigby believe the drop in oxygen levels is what slowly killed off the dinosaurs, while sparing other creatures, including mammals. Their theory includes recent studies that suggest dinosaurs may have lacked a diaphragm and relied on their giant chest muscles to flex their rib cages in order to breathe. The method was inefficient, but in an oxygen-rich environment, that wasn't a problem. As the air became thinner, however, the dinosaurs began to suffocate.
They were unable to move as rapidly and unable to chase down and make their kills in food. They were less capable of migrating to new pastures for grazing, for feed. You might even speculate that an animal having difficulty breathing enough to maintain its normal activity would be far less interested even in sex and reproduction.
Meanwhile, small mammals prospered. They had a muscular diaphragm beneath their lungs that helped them breathe the oxygen-depleted air. Smaller reptiles without diaphragms hung on because of their lower metabolic needs. But what caused the oxygen level to drop? According to Rigby and Landis, in the middle period of dinosaurs, the Jurassic, Earth's land masses were rapidly shifting, causing great volcanic eruptions and earthquakes. The violent activity pumped large amounts of carbon dioxide into the air, which the trees converted to oxygen. It was a lush, oxygen-rich environment in which the dinosaurs thrived. Then, in the Cretaceous, land mass movements slowly settled down. With fewer eruptions, less carbon dioxide was spewed. Plant life withered, and oxygen levels dropped. Slowly, the dinosaurs died out. By the time the asteroid hit, the damage was already done. While the oxygen theory is controversial, many paleontologists agree that slow-acting, complex environmental changes contributed to the dinosaurs' demise. Even so, it can't be denied that dinosaur remains vanish from the fossil record at the same place that marks an asteroid impact, and evidence continues to mount that links the two events. Vast craters that scar the Earth's surface show that debris from space has pummeled our planet more than once. Scientists who keep an eye on the far reaches of space consider the idea of a killer asteroid wreaking havoc on our planet as a very real threat, even today. Could the human race become just another statistic on the extinction chart? Would a giant asteroid come flying out of the sky and wipe humanity from the face of the Earth? Are we doomed to suffer the same fate as the dinosaurs? Some scientists are taking the threat seriously. At Kitt Peak Observatory near Tucson, Arizona, Jim Scotty is one of the astronomers who run a project called Space Watch. The team operates a telescope that keeps an eye out for asteroids and comets approaching Earth. Scotty has seen enough of them to be worried. To recognize impending disaster as early as possible, he bathes his telescope with liquid nitrogen to minimize distortion. The telescope automatically rotates throughout the night, constantly scanning the skies for asteroids or comets that might be headed our way. The view is recorded by a sensitive electronic camera attached to the telescope. The images are fed into a computer, which picks out the fast-moving asteroids against the background of stationary stars and planets.
On our computer screen, the slower-moving main-belt asteroids are indicated by flagging them with boxes and numbers indicating where the object is in the current image and was in the previous two images. Our computer software finds literally hundreds of main belt asteroids every night, but we're after the fast-moving asteroids that are potential Earth-crossing asteroids.
So the Space Watch team gets worried only if the computer tracks a rogue asteroid that's been kicked out of the main asteroid belt between Mars and Jupiter and is heading toward Earth. They're finding about 3 a month. What are the chances we'll get hit? In fact, meteors, commonly known as shooting stars, hit us all the time. They're pieces of space debris smaller than an asteroid, but anything up to the size of a house will burn up in the atmosphere. A 100-foot asteroid strikes about once a century. That's what blew out Meteor Crater near Flagstaff, Arizona, 50,000 years ago. As for a 6-mile-wide dinosaur killer, fortunately, scientists think it's a rare event, maybe once every 100 million years. But there's another threat to worry about: comets. These icy masses don't orbit the sun in a well-defined belt like the asteroids do. Many swing far out to the edge of the solar system beyond Pluto. They're fast-moving, so they can appear out of deep space with relatively little warning.
An object the size of the dinosaur killers, something like 10 or 20 kilometers in diameter, would be visible to our telescope with our current technology probably for only about a year or two.
Astronomers only had a 16-month warning when fragments of comet Shoemaker-Levy were spotted heading toward Jupiter. In July 1994, the telescopes recorded the impacts. The biggest was equal to a 1 million megaton bomb, leaving an impact site the size of planet Earth. What could we do if we only had a few months' notice of such a cataclysmic threat? With present technology, there's not a lot we can do. There are plenty of ideas about how to defend ourselves, like sending a nuclear bomb into space to blow it up.
But no matter what you do, you don't want to blow the asteroid to smithereens. That's not going to help you, because instead, you're not going to vaporize the asteroid, you're going to make it into a big rubble pile. And it's still going to hit the Earth.
It may take a more subtle approach to nudge an asteroid out of the way, maybe using microwave beams or solar sails. The Spacewatch scientists think we should be trying to solve the problem.
Dinosaurs lasted for well over 100 million years, and they endured at least one other big impact event. But during all that time, they never quite got around to building an asteroid deflection system. So look what it got them. It got them fossilized.
Even if humans had been around at the time of the dinosaurs to develop Star Wars technology, we might not have saved them. Though new evidence strongly suggests that an asteroid was the agent of death, the dinosaurs may have already been on the way out, endangered by millions of years of global change to which they couldn't adapt fast enough. Or perhaps they dropped in droves from disease. For now, the dinosaurs' extinction remains a compelling mystery. But scientists are learning more about the forces of nature that caused it. Maybe one day they'll put all the pieces together and in the process gain insight about our own future.